spoke at the ISDC last year in Toronto. He's been working on different projects. He's basically involved on his own as an independent science writer. He's been involved in some investigation of different technologies. And it's all of that leading edge that Mark's going to address. What if, what if, this, and raising questions. He's going to do a presentation through that, and get you thinking about the future. And he's going to give us a presentation today to make us think and ask questions, and we'll give him enough time in the question and answer section. And I wanted to note after this that Dr. David Webb also will be our speaker at the supper for us today. It's been really well so far, and Mark's going to entertain us before, and it's titled, I don't want to plug this up, it's the PROTON SUPERLUMINOSITY. All right, that sounds like the rollerblade and everything else all rolled into one.
Just about.
Go for it. Well, we welcome Mark. Let's give him a big hand here to bring on.
Thank you. Yes, the title of this presentation is Proton Superluminosity. That means going faster than light. And that's protons, not tachyons. Proton superluminosity, smashing the light barrier. Not going to nudge it, not going to get a little bit past it. Going to knock it out and go for the big time. People like to talk about tachyons and wormholes. I was talking to a gentleman on the phone who said that out here at one of these NASA installations not long ago, they had a meeting with a lot of their bigwigs about how to go faster than light, and they talked about tachyons and wormholes. And I said, oh, I've been hearing about that since I was in elementary school, and I'm 42 years old. And he said, oh, no, this is cutting edge stuff. I went back and got out my little old dusty brown satchel I used to carry to elementary school back in the 50s. And I opened it up and I pulled out this old crumbly weekly reader dated February 1959. I think it was February, March, one of those. It's a 59 issue. And I opened it up, and the scientists were talking about, I'll give you three guesses, tachyons and wormholes. Let me tell you something about tachyons and wormholes with respect to the so-called, notice I say so-called, light barrier, because I no longer believe in it. I think it's hogwash. People think what I believe is hogwash. I say light barrier is hogwash. But I'm going to try to convince you. Here's this light barrier. You see it, don't you? Well, the two guys standing here, they believe it's there. You know the story about the emperor's new clothes? Okay. I go over here to this one fella, and he's digging a hole. And I say, excuse me, what are you doing? And he says, oh, I'm digging a wormhole. I'm trying to get around the light barrier. The what? The light barrier. It's right there. Can't you see it? Wait. Right here. That? Yeah. I can't get past it. I'll take your word for it. That's what they did in college. Somebody told them it was there and they believed it. That's what they told me when I went to college, and I believed it for a while. But when I started to research the assertions behind it, that's exactly what they were. Gratuitous assertions. Well, there's another fellow over here. He's got a little apparatus. He's trying to detect some particles. What are you looking for? Tachyons. What are tachyons? Well, their particles go faster than light. They come through this here barrier. What barrier? The light barrier. It's right there. Can't you see it? Sorry, I don't see it. That's my view of the light barrier in a nutshell. That's my view on tachyons and wormholes. If anybody wants to bring up the subject so you can forget about it during Q&A, okay? That's how I kill that up front. You see, in Toronto, I did this paper called The Light Barrier Factor Fallacy. Three guesses which of the two it was, right? Fallacy. As a matter of fact, my first 3 or 4 slides here are taken from part of that presentation, where I basically show that there is symmetry breaking in mass energy, which was the backbone of the idea of the light barrier in the first place, using a Newtonian approach. which had to do with an object being self-propelled like a rocket, but the mass had to be consumed, and even if you could consume all the energy, the atomic energy, the nuclear energy, which they had just discovered was there, not just chemical, but nuclear energy, and then break all that down into pure energy, whatever that means. And I'm still trying to figure that one out after all these years. Then, by the time you got to anywhere near light velocity, there wouldn't be any mass left. Which befuddled my mind no end when they told me that as you approach light velocity, the mass increases. You know, of course, there's more reasoning behind that has to do with linear accelerators. Now, in Toronto, during the Q&A, I had a critic. There's always a critic. I would call this man a heckler, but he was very polite, being British. You know, over there, when they rob banks, that if it's 4 in the afternoon and Big Ben sounds off, they all stop and have tea together and then continue the robbery. They're very polite, you know. Yeah, the robbers in the box, they all sit down and discuss, you know, how mom's doing. Mum, excuse me, for those British folks. Well, this guy had a heavy, you know, London accent, it sounded like to me. But he proceeded to beat me over the head with the evidence of linear accelerators. As you try to accelerate the particle more and more, you have to put in increasing amounts of energy and you get less and less acceleration as you approach C. Well, I've just been talking about symmetry breaking. C is not even constant. We have data right now. Dr. Tom Flander over the National Laboratory in Washington, minute by minute, is tracking variations in C against their new laser clocks. It's going down with a wiggle, some kind of modulation, which I speculated might be due to the oscillation of wormholes. You see what they've done to my mind? Excuse me, black holes. They've affected me. I can't get wormholes out of my mind. They've got wormed in here, wormed their way out there, you know, in one ear and out the other. The worm goes in, the worm crawls out. You know that song? Oh, college destroyed my brain, believe me. But anyway, he beat me up with his linear accelerator evidence because my paper didn't talk about it. I talked about the data, and I talked about the broken symmetry and mass energy. He inspired this paper. This slams the door shut on the topic once and for all. I might as well get down to it before I burn up too much more time with my little anecdotes, right? Not that I don't have more coming. I think of them as I go. Believe it or not, I don't prepare this. It just happens. Harvard says. Hey, it works. You know, this is my third ISDC, and this is the first time I pushed the button for that thing, and it worked when I did it. They blew it in Huntsville, they blew it in Toronto. By God, these folks got to give them a hand. Congratulations. AV, 2 points. This is a little trick I thought up, which has to do with representing light velocity as an in-vector in an in-space. The in-space can be whatever you want. It can be Einstein metric. It doesn't matter. And so what I do is I take an n-dimensional matrix A, rank n, an in-vector V, and some real number lambda, and I take what's called the eigenvalue, eigenvector relation, or Markov process, which, of course, that's normally for just an eigenvalue of 1, whereas here, the eigenvalue can be whatever. And I do some dot product. I dot V into both sides, and I reduce it down, and you get some real number S is equal to lambda times the square of the magnitude of V. Now that looks suspiciously familiar to something, which people are always talking about, E equals mc squared, right? And special relativity, the mass energy relation, the backbone, as I said, of the idea behind the light barrier. Now, it just so happens that most mathematicians are aware, and there's a formalization of this statement, I forget how it goes exactly, but what it amounts to is that if you have 2 equations of the same identical form, they have identical properties, and they can be derived by identical means, which means you could say that this is the mass energy relation. So we just make a substitution, and there it is. And now we look at the properties of each of these values. Energy is simply a real quantity. Mass is an eigenvalue, and that has all sorts of strange implications. And C is an eigenvector. Now, after doing a little mathematical trickery, I'm glossing over the points here, we look at the four possibilities we can get when we take the magnitudes of these vectors, just the magnitudes, not their squares necessarily, and plot it against time to see if light velocity is going up or down and whether or not it's modulated. And I had some conditions I applied to make sure we'd have at least 3 viable eigenvectors we could use out of any given eigenfield, so that if there was a twofold variance, which is what I was looking for, that it would show up, and it did. And it just happens to be the one in the diagram on the right. Light's going down over time with a wiggle. Matter of fact, I can read you the formalization real quick if there's anyone who would just like to hear that curiosity. A review of mass energy symmetry breaking. This is read from the paper here where I reproduced it from the other paper. Let us assume there exists a matrix A of rank n, a non-zero input vector v, a non-zero real number h, which I use for lambda here, such as AB equals lambda v, for which we will add the additional arbitrary constraints that for any given real constant k and r, there exists no vector such as no vector v equals v sub I, such as v sub I is equal to some k in r times some v sub j. And the magnitude of v sub I is unique for every vector v sub I across the eigenfield of eigenspace e of lambda, for which 2 is less than the dimension of the eigenspace of lambda, which is less than or equal to n, for which the magnitude of v sub I denotes, okay, this is explaining the notation I had here, because I had used some little funny characters because I didn't have absolute magnitude bars in the computer, so 2 little vertical dashes, and this was explaining about that. V sub j is any other vector occurring across the entire eigenfield of the eigenspace E of h. To derive the mass energy relation, we begin by dotting the vector v into both sides of the eigenvector equation as I showed you and reduce it. Then we equate it to mass energy. And it says we see immediately that energy is a simple real quantity, mass is an eigenvalue, and light velocity is an eigenvector. We can begin by dispensing with the more trivial observations about vectors, the magnitudes of which will satisfy mass energy relation for any mass eigenvalue, or for that matter, a Markov relation where lambda equals m equals 1. We are concerned with the non-trivial cases which meet the original constraints on the eigenvector v and therefore on C, as stated at the beginning of this section. More importantly, we are concerned with cases for which the geometric multiplicity, or the dimension, of the eigenspace of mass E of m is greater than 2. To simplify the consideration, we will assume that geometric multiplicity of E of m is equal to the algebraic multiplicity of E of m, so that no eigenvalues are repeated. So we're going to get no less than 3 distinct eigenvectors. That was the idea, because you're going to have a minimum of 2 eigenvectors for any given eigenvalue. The trivial case, which is the 0 vector, which would work for anything, and 1 non-trivial, whatever that would be. And so that's where that came from. Now, then we plot light velocity against time using the magnitudes of the eigenvectors from the evaluation of the null space E of m for the non-repeating eigenvalues obtained from the evaluation of the characteristic equation, which is that determinant. Then we obtain a function plot which, under our chosen constraints, must meet the following conditions. No plotted points will have the same ordinate or y value, which none of those did, and the function plot must be generally increasing or generally decreasing. So in other words, it's going up or going down, with or without a wiggle. It's going down with a wiggle that matches the data. That's what we have. So I have found a way mathematically to represent it, and that's what the first paper was all about. Then came the heckler. A British fellow, Walt, beat me up. And I was up there doing this for 2 reasons. Number 1, he got me. I didn't have anything in the paper about linear accelerators. And number 2, I figured I deserved it for not thinking about it. So, I went on and said, let's look at what happens in linear accelerators. But let's stop and consider something called supersymmetry. Now, I've done a lot of work with something called the Newman machine. People think that is a hoax. They say, oh, free energy. Oh, no, it's a perpetual motion machine. No, it uses supersymmetry and broken symmetry. There is an entropy path from, apparently, the weak nuclear field by the electron-weak interaction to either charge or spin of an electron, from the spin to the magnetic field, from there to the external world. The man found it. When you take a declension field, that's a collapsing magnetic field, and you have a mutual field interaction, and the load on that inductor increases. If there is an energy source through which a supersymmetry will allow the broken symmetry in spin to transfer energy to the outside world, it will. That's what's happening in the Newman machine. Now, this sort of thing has a lot of application to magnetoplasma dynamics. I'll be talking about that Sunday with plasma thunder, Mars in a week. You can actually get there faster than that. But yeah, dangerously so too, I might add. Especially if you don't break in time. You'll miss it and end up at Jupiter in about another day or two. But what it is that this supersymmetry is something which allows us to take a new look at what is actually happening in a linear accelerator. Excuse me, I bit my tongue there. In linear accelerators, when they accelerate a charged particle, now stop and think, that's a charged particle. They don't do it with neutrons, do they? You see, that's one of the things that always bugs me. I stop and say, what about particles with no charge? They have no magnetic field, no spin, no net magnetic moment. Oh, they don't have that kind of data for kind of particles. Only for charged particles, something they can accelerate magnetically or electrically. So we can deal with the broken symmetry there, can't we? I see. The traditional view of what happens to charged particles in linear accelerators goes something like following. Energy from the linear accelerator is imparted to the particle. A primary field causes acceleration by one of the applicable laws, law of electrical charges, that sort of thing. As the particle accelerates through the relativistic regime, this is arbitrarily set. That's another one of those little things that bothers me. They just arbitrarily decided anything above 0.1 C is relativistic regime. And I thought, oh, hey, that's interesting. I wonder what the reasoning was behind that. Answer, there ain't none. They just stuck it there, pin the tail on the donkey. 0.1 C, hey, that's relativistic. Oh, love it. Its mass and half-life both increase. Well, half-life increases, yeah, they can demonstrate that, but the mass increases? Interesting. As the velocity of the particle approaches c, the mass of the particle approaches infinity. The opposite of the case I was talking about, where you have a self-propelled particle and you apply the mass-energy relation, which is the way they looked at it in the old literature if you go back and read it. Because you see, Newtonian concepts were the only things with which they had experience up to that point. They had to think in terms of a cannonball or a rocket. They had nothing else to use for a reference. So what if there's really something else happening here? Because they say that the extended half-life is due to time dilation. Oh, that's another thing that fascinates me, knowing time dilation. Einstein had this so-called Gedanken experiment, a thought experiment. I kind of wonder if he was smoking, drinking, or whatever time that he was thinking about this, where you're running alongside a light wave and you've got an image of a clock face and it says 8 o'clock. It's running ahead of you, but you run along there, you catch up to it, and you're running alongside it, and you're running at the same speed it is, so you're going at C. You look at it, it's 8 o'clock. Well, you're running and running and running. What time is it now? Well, it's 8 o'clock. Running and running and running. What time is it now? It's 8 o'clock. Time's frozen. What happened? Well, the time just dilated. Did it? Because after all, how did he see that light wave? Because the light wave's got to get somewhere for it to be seen, right? That's one of those little things that just bugged me. Now, his experiment struck me as incomplete. His Gedanken experiments, anyway. But this was the basis of the idea of time dilation. You see, if I had been sitting in a class where Professor Einstein would have brought this up, I would have said, "Excuse me, Professor, what happens to time in the dark?" I think that would have shot the biggest hole in that. It's like, Lord Kelvin talking about when you can express something in numbers, you can begin to know something about it. I would say, "Excuse me, Professor Kelvin, what are you quantizing?" Qualitative aspect is something that cannot be forgotten, But these people teach these things as if it's, magnificent theology, more than philosophy. And I go, you forgot something here, sucker. Enough digression, right? I see I'm boring the tar out of poor people. A few people are laughing, the rest are going, come on, get the point. Okay, forgive me. Charged particles as saturated reactors. let's look at a charged particle as a saturable reactor. Now, what am I talking about? I was just talking about supersymmetry. A supersymmetry is something that takes over if you have a symmetry break. A symmetry break is something which occurs when you have a conserved quantity like charge or spin that no longer behaves as a conserved quantity. Like in the Newman machine, electron spin must be conserved. Well, if you're talking about symmetry, yeah, it better be conserved. Otherwise, all of, quantum physics and classical physics will collapse. Unless you have a supersymmetry to deal with it. And if you do, then, spin can be doing all kinds of things. Energy can be going to and fro like you wouldn't believe. This is a diagram of something called a transductor or a saturable reactor. This is the device which I use as an analogy to proton spin, which is a coupling to the magnetic field, just like electron spin. And the two can, in fact, interact that way using what I call spin torque. A lot of people call it that. And you'll notice that we have 4 windings on this toroidal core. Now, the top one is labeled gate, lower one's bias, current in and current out. Current in and current out are writ large because those are large currents. They are varying currents. Bias is fixed. Gate varies, but bias and gate are both relatively small. Now, bias is used to establish an initial condition in the transductor for which you have a small magnetic field already built up in it, but it's a steady field. Now, when gate comes in, what happens is if you have a current coming in IN, which is some sort of signal. No, excuse me, I've got that backwards. Gate is varying IN would be fixed, and IN is large. Gate comes in here, and it's a small signal. What's going to happen is you're going to get a large signal variation at I out. But bias sets your initial condition, which allows you to do this. Otherwise, gate wouldn't be able to affect the coupling between IN and I out. Excuse me, IN is fixed, just like DC. I out is going to be a large version of what's coming in at gate. This basically is what's called a saturable reactor. And the saturation point can be varied by varying this bias. Now, when we're talking about a proton, you notice here I have a sort of a similar looking diagram, but at the top I have it labeled induced or forced broken symmetry. Now at the bottom I have charge spin symmetry. Over to the left I have E for energy from a linear accelerator. Oh, sorry, I thought that was bolted down. I see it isn't. And I have on the right energy of supersymmetry or a supersymmetric field that can be built up about this particle. Now what I'm saying is that what actually happens in linear accelerator is that when you apply the primary field of the accelerator to the proton, you induce a forced broken symmetry in charge or spin or the coupling between them. You cause symmetry breaking in spin and or charge, but spin is what we want to look at because that's our magnetic coupling. And we'll assume we're using magnetic acceleration, which most of these do, like for example your bevel lag, and we'll look at the construction of a linear accelerator here in a moment. Now, when this symmetry break occurs, you have this induced field stress within the particle. It's got to be relieved, so it builds up a supersymmetric field to relieve this stress. The energy from the accelerator's field went to the supersymmetric field, but as soon as it did that, the saturation point for this thing has changed, and the particle moved because the supersymmetric field is reactive, and it fights the accelerator as the particle accelerates. Now, as the particle goes faster, the supersymmetric field gets stronger, becomes more reactive. It takes more energy to accelerate the particle. Also, at the same time as the supersymmetric field builds up, the increased energy of that field contributes to the half-life of the particle. Nothing's happening to time. There isn't any time dilation. is supersymmetric field energy coming into play. The particle is not gaining mass. Of course, most people who deal with that sort of thing on a day-to-day basis have pretty much come to agree among themselves that mass is not really what increased. There is some sort of field energy, reactive field energy present. And if you look at your, I forget, Taylor, McLaurin series, whichever it is, where you express relativistic mass in terms of an infinite series, that you're actually looking at energies. Because, like, for example, your second term has the format of kinetic energy. You know, you want to have mv squared type of term. So, you have built up the supersymmetric field, and it's very reactive. You get very close to C, and the amount of energy necessary to accelerate the particle becomes just utterly unavailable. But I'm saying that this is an artifact of electromagnetics, of electromagnetic theory, and it's not because of time dilation or relativistic mass. The M0 has not in fact changed. You build up this supersymmetric field, and the field in turn is also contributing to the increased half-life of the particle. Now, if you stop and think in terms of Lenz's law and an inductor, when you have an expanding field, you have a counter EMF. That field resists being built. And if you have a mutual field interaction, you're going to get even more resistance. I mean, you're going to get a whopping counter EMF. Now, the same thing holds true in reverse, though, because Lenz's law has two parts. When the field is collapsing, you have co-EMF. And if you have a mutual field interaction, those fields work together. And if, like in the Newman machine, the load is zero, which it is periodically during the rotation of the machine, which he achieves with his commutator, which I'll show you with a little schematic here shortly, then you get something called mutual field hyperdeclension. And you get a whopping co-EMF, and you get a net energy transfer from whatever source will deliver through or by way of the supersymmetry to the external field into, in this case, a coil in the linear accelerator, which is one that we're going to add on to it, because we're going to look at how to modify one of the machines in order to make the proton dump its supersymmetric field energy, which is going to make what appears to be the relativistic mass, which is what they're measuring, that resistance to acceleration, actually, because of the reactivity of the supersymmetric field. And it's going to drop to M0. The half-life is going to drop to normal. But what's the particle going to do? It's going to accelerate. Hey, but it's already right up by this barrier. And it's going to accelerate? What kind of acceleration are we going to get? How do we determine it? That was another question I got hit with. How do you determine how fast the particle is going to go? What's going to be the final velocity? Believe it or not, you use Newton's third law because you're looking at energy transfer. And you can look at the relativistic mass. I'll answer the question shortly. Keep it in mind. The relativistic mass is an expression of that build-up energy. You take the ratio of m sub r to m0 times the velocity of the accelerator, and that's going to be the final velocity. And if the v sub a for the accelerator is like 0.99228 c, I've done this calculation with this particular number because I wanted it to come out to this, then the final velocity is going to be 8c. For you Trekkies, that's warp factor 2. I find it fascinating that in the old television series you talk about how the early warp vessels were limited to warp 2. I thought that was a fascinating coincidence because a little past warp 2 is what you would get with the technology we have available. I mean, it's either a whopping coincidence or Gene Roddenberry was more of a prophet than anyone imagined.
Or he did some of the same homework you did.
Possible. Talk with some of the same aliens, maybe? No.
Supersymmetry field.
Hmm?
That supersymmetry field, it's building up.
Yeah, it's
It's building up by the symmetry breakdown.
Yeah, you say, okay, but when you force the symmetry break, in other words, what it is you have, okay, electromagnetic theory is the unification of charge, the law of electrical charges and the, basically your laws of magnetics here, right? Yeah, it's unification of magnetic and electric fields.
So is the symmetry breaking a little bit at a time as you're
Well, yeah. I mean, it's a continuous process, but you look at it stepwise to see how it works. but it's a smooth and continuous type of thing. You could probably quantize and break it down in little tiny steps, but I've thought about it that way, and I don't see the point in doing it. There's no reason not to think of it as smooth and continuous. So this is, again, quote, field theory, end quote, even though the concept of supersymmetry comes from quantum mechanics, so that's kind of an odd marriage there.
So it's not just coupled and decoupled, coupling and decoupled.
Oh, no, and what's happening is things are changing continuously. You apply the acceleration field, this induces a force-broken symmetry, and the supersymmetric field builds up to relieve the induced stress. The particle accelerates, and at the same time the field becomes more and more reactive. And that reactivity is, quote, misinterpreted, end quote, as relativistic mass, and the extended half-life, because of the build-up field energy, is misinterpreted, I say, as time dilation. And the fact that the thing gets so hard to accelerate at c is just an artifact of the theory itself. Yeah. So because, we look at the wave velocities and electromagnetic energy right about c. Of course, like I say, c is varying over time. The cosmologists are tearing their hair out over it, And of course, it depends on which area of physics you're in. You go through different fields of physics, and you can rate them according to the length of time it takes them to come around to accepting the evidence. The cosmologists are usually first, and the astrophysicists, for some reason, tend to be last. I don't know why that is, but it is true most of the time. Not always. There are exceptions, but it's usually true. Let's look at the linear accelerator itself. This is a typical machine. You have some sort of proton source here, for example. You have a gadget called a bevel-ack. The way that works is to take a magnetic field and use it in much the same way they use it in a tokamak, really, to accelerate the proton. This field builds up very rapidly. The proton goes round and round, and it comes out here, It's because it looks kind of like a horn when you stop and think about it. Then that accelerator tunnel is a combination of electrostatic and electromagnetic, devices to give it the final kick, down to the little target T, where they have some sort of thing that looks like a music stand, holds a little card of some material, and it strikes that, and they get bursts of various particles that go down various paths, and you have the different detectors, sensors, and so forth down there. And that's what a basic machine looks like in terms of a very rough diagram. Now let's look what a modified machine looks like to do what I'm talking about. You notice we took out the target, and we put in a hyperdeclension coil. That's hyperdeclension is what I call field declension or collapse into a short circuit, particularly if you're talking about a coil which has been subjected to reduction to a superconductor, so that R Thevenin's been eliminated. Now in your relation T equals L over R for you engineering types, you have two non-removable discontinuities, remember, that you have to deal with, and that's R at infinity and R equals 0. Now, as R approaches 0, T is getting larger and larger and larger, but when it hits 0, it goes whammo. Does the same thing it does out at infinity, or at least that's what the operation of the Newman machine indicates. So, it does. In other words, you would expect to see something like what they call flux trapping in magnetic levitation, but now what do? To get the trap flux out? They use a mutual field interaction, right? Move it around, get it out of there. And what happens when it reaches a point where that trap flux can go to an external field through the mutual field interaction and go to a load somewhere? It goes zap right out of it, right? Dr. Bill Hamilton does that with that aluminum bar of his, 11,000-pound gadget he's using to try to detect gravity waves down at LSU Baton Rouge. Down there in the basement of Nicholson Hall, I went down there and visited that. It's a very interesting device. And they have lots of little problems with levitation, but it's quite a project. And there's a lot of insight to be gained from the problems they've had with the magnetic levitation. But basically, you don't get this flux trapping phenomenon in this case where you provide the complete circuit here. So we supercool these coils and get these things down to the point that they're basically superconductors. And notice that the switch down here is set up like that little sub-schematic at the upper right. Your proton comes through here and your coils are arranged in such a way. And this thing, by the way, can be as short as 1 meter and pull this off. The time in which the field's going to have to collapse, and it will do it, is basically twice the length of the coil divided by the delta V to be achieved, which is a little over 7c. And so your proton comes through here, you get your mutual field interaction. The magnetic moment starts to rotate the proton as it comes in here, and you've got a steady field already built up waiting for the proton. When it gets there, it hits that, and as soon as you get the reaction between the two, short the coil, you got to time it just right, and this thing's going to dump its supersymmetric field energy into that coil, and go to 8C, assuming it entered at 0.99228 or thereabouts. And what I'm going to do to measure the velocity, that was another question related to that first one, how to determine how fast it would go, is to have a water trough of suitable length with radiometers or radiometer type detectors at intervals down it, which are all synchronized with WWV or WWVHCHU or whatever's handy, with the time correction, you know, for the separations, multi-path, signal problems, all that sort of stuff they have to work out. It's like when they're synchronizing gravity wave experiments around the world, the same kind of problems they have to solve for that. And you're going to get this burst of radiation at each station very, very quickly, which will create a bell curve, and the center of the bell curve is the time at which it passed that sensor. And you can go back and compare that to your calculation. And the calculation basically is that. The one at the top is Newton's third law. Relativistic mass times the velocity of the accelerator, which is whatever the accelerator can achieve, is the m0 times the final velocity. And of course you can solve for the v sub f. Your relativistic mass is calculated like this here. This is just standard formula. Notice that is the v sub a down there under the radical. And this is where we've solved for v sub f, and there's a trough, and there are little bell curves. And there's our 8C proton going in. Now, the only thing left for anybody to do is to try it. I've shown how, I've shown the schematics, I've shown the calculations, there's very little to it. It's a matter of reasoning it out. Hopefully sometime this summer I'm going to have a mail-out campaign to the top 100 linear accelerator laboratories around the world, with the exception of the Middle East. Unfortunately, I will exclude Israel to be even-handed about it, because we don't want Saddam Hussein getting hold of this kind of technology. And what I'm going to do is I'm going to send them a cover letter, a copy of this paper and its predecessor, and a list of all the people who got it. Some people are going to take it, look at it, throw it in the round file. Some people will actually take it out of the envelope, read it, and throw it in the round file. That's probably going to be 80 and 90% off right there. And that's based on 25 years experience, trust me. But those precious few are going to take it out, look at it, and go, my God, we've got to do this before they do. And it's going to be a race to see who can do it first. Some 3 or 4 people somewhere are going to take it out and do something besides kick it around and ultimately to the trash can. There's going to be this bevy of guys running down the hall screaming, waving this paper saying, we've got to do this now before the Russians do, or the Chinese, or the British, or somebody. And 2 or 3 of them are going to try it. I was originally being coaxed, cajoled, driven, arm twisted a little bit here and there, to try to sneak in the back door of one particular laboratory like Fermilab, talk to Bill Higgins or somebody like that, and kind of try to sneak my way around to the front office and go slinking in with my paper and say, would you like to try to drop the proton to 8C? You know how fast they call security and bounce me off the premises if I did that? Now, I decided the mail-out campaign would be much better, because then it's like when you're trying to sell something and you've got only one buyer. You're at a disadvantage until you've got 3 or 4 buyers that want it, especially if one of them's a plant and you're trying to outbid everybody else. You get action then, and that's the approach I've decided to use. So, hopefully, in the not too distant future, you will see not only probably a little written commentary and a newsletter here and there about this nut Mark Schultz got up here talking about driving protons faster than light, doesn't believe in the light barrier. Can you imagine such nonsense? Followed by a blast of news reports from around the world of the successful driving of a proton to a little over 8C by certain laboratories. And then maybe you'll see me on the cover of Newsweek. You know, I like to think of these things in terms of my personal aggrandizement. You know, oh man, I don't know. I'm not sure if I can handle fame if this actually came to pass. You know, when I think of what happens to famous people, I kind of halfway hope this doesn't work, and I'm totally wrong. But I hate to say I've done the research and I believe it'll work. Are there any questions?
Sir, do you publish this stuff anywhere so that it can be peer reviewed?
That is something that I have had suggested to me, and I have been at a loss as to where to send it, because I used to talk over the phone. I never met the man personally, but to Dr. Erwin J. Saxel, who was widely noted, but he was a postdoctoral student with Einstein, by the way, in the 50s. And he did an experiment with an electrified torque pendulum, which showed a square law relationship between voltage and gravitational acceleration for a torque pendulum in a Faraday cage with an equipotential apparatus. And one of the comments, choice comments he had about the referees of the various journals is, and he said, and this is a quote, and it's the way he said it, "So if you are very harsh," end quote. I never forgot that. It rings in my ears to this day, because I asked him about this unpublished paper that he had, and I said, "When are you going to get this published?" And it was a couple of seconds of silence, and then that statement. I never, ever forgot that. And that was about 15 or so years ago. And the gentleman is long since deceased, but he was one of the people I read about in books where I was reading up on gravitation, another one of my interests. And it was in a book about UFOs, of all things, because I was interested in that when I was younger. Of course, now I'm interested simply in advanced propulsion. But my idea of advanced propulsion is, can you walk under it while it's hovering, and can you hear a pin drop? You know, when you can do that, it's advanced. Yes?
Yeah. Maybe you explain this somewhere else. Where does Michelson Morley start?
Michelson Morley, basically, what the ether, they were both ether theorists, by the way. What the deal was that Professor Michelson was from the University of Chicago. That wasn't where they did the experiment originally, although they transported the apparatus around the country and it was there at one time. They did their experiment in the basement. It was a small baseline machine. It was set up on a card table, very flimsy apparatus. It could not really see down to the order of magnitude that was necessary to look for the sorts of ether shifts they were looking for. Dayton C. Miller, Cantor, and a bunch of other people with huge apparatus up on mountaintops did see it, but they got shouted down by the majority who did the comparatively poor experiments, and all agreed with one another that they didn't see anything, because basically they all had their lens caps on, Yeah, the Miller and the others had their telephotos and they had the lens cap off, and so they could see, but that's, a euphemism, but still.
Are you saying that experiment should be re-performed?
It was. But Miller's was vastly superior. Dayton C. Miller, you should read up on him and read up on, I forget Cantor's first name, but he was from, I think, San Francisco. Miller and Cantor were two of the very best. But there were several others. There were, I wish I had their names handy. They're in my other paper. I have copies of those papers here if anybody wants reproductions. I brought them all. And anybody who wants copies of them, I'll be happy to provide them. Oh, by the way, something else, I would like to get a mailing list. Anybody, if somebody can come up with a sheet of paper, I bet to come in here with a spiral notebook, and you can put down your name and address and so forth, and I will add you to my mailing list. Anybody who wants to get on my mailing list for material of this type, and I send out copies of the papers from time to time.
If you're interested, you can do that at the registration desk. Answer other questions. Okay.
Yes?
Going back one slide, go back one slide, you're calculating your relative mass, but you're dividing by c, by the c squared. In that function, when you started out by saying c is not constant. So how is that going to be affecting your calculation?
Yeah, that's, I'll put it this way, the F minus, magnitude of F minus epsilon is small. Or would that be delta? I forget. The interval of variation is small. You see, that's why for a long time it's been difficult to convince people that the variation exists, because it's such a small variation. But you see, today we have apparatus that can track it moment to moment. And when this sort of stuff was first being written about, they didn't have that kind of technology. What they did was they went back and studied the data over decades and decades. Like for example, there was this paper published in the journal Galilean Electrodynamics, which, as a matter of fact, I've got a reference to it right here. Let me see. The work of Montgomery and Dolphin, published in Galilean Electrodynamics. Okay, Montgomery's in Canada, Dolphin's in California. Published in Galilean Electrodynamics, has provided strong verification that light velocity is indeed decreasing over time with the overriding observation that atomic and dynamical clocks apparently do not run in step, which has been a widely held belief up to this time. The same sort of thing's happening with the gravitational constant, which ties in with the comment I made about how black holes can be oscillating, but then this runs into what you might call the chicken and egg problem, because are black holes all over the cosmos oscillating, and this is affecting light velocity, or is it the variation in light velocity that makes black holes appear to oscillate? They're doing this as they grow. The Schwarzschild radius has to be moving with light velocity because that's what determines that radius. So, that's an interesting little problem there.
Other questions, please? Well, we thank you very much, Mark, for this presentation. For this, and we'll have a question like the Mark again.